I would like to thank EMTP team to give me an opportunity to share my experience in fall user conference. I would also like to thank my organization to give me an exposure to participate in this conference. The topic of the presentation is Ferroresonance Phenomena for VT failure, followed by EMTP simulations and the mitigation technique. Well, it is a mixture of the field observation, the phenomena experienced, and the various simulations analysis performed in the EMTP software tool. So this will be the content of the presentation. We will see the phenomena in brief, and then we'll go through the case study and the failures of the EMVT failure, which has been experienced, and little bit of the RCA. Then we will see the ferroresonance phenomena slightly in more detail and how it can be mitigated or prevented. Then we will go through the EMTP application simulations, which we did, and we will see the result waveforms. And finally, what kind of mitigation we did and implemented in that particular power plant where this phenomena experienced. So this will be the flow of the presentation. And finally, we will conclude the entire phenomena. So as we know, the ferroresonance is a complex electrical phenomena that though identified since the early 1920s, but still it is remains a little understood even today. The ferroresonance has been known to be responsible for equipment damage and the protection malfunction. It is hard to analyze in part because it doesn't occur regularly or predictably. So ferroresonance, we can see, and it can be usually characterized by the over voltage and a very irregular wave shape. And it is associated mainly with the excitation of one or more saturable inductor through a capacitance, either in the series or in parallel with a nonlinear inductor. This phenomena can occur when VTs, these EMVTs are connected in phase to ground in ungrounded system or a highly resistive grounded system. The saturable inductor is usually present in a form of instrument transformer or can be a power transformer or a reactor, which contains mainly iron core, which is a ferromagnetic material. And this particular phenomena of ferroresonance for a single pole insulated transformer in unearthed network is most common phenomena observed. Now, depending on the supply voltage or capacitance and the inductance, these oscillations can be either periodic, can be over or subharmonic, or maybe the fundamental frequency, or can be aperiodic. Now, in past, 4 incidents of voltage, or we can say the potential transformer EMVT failure, which is connected to the generator phase duct, were observed. All the EMVTs which are failed, mainly identical in nature. Now, if you see in this frequency resonance, the voltage is usually not high, but the current of the PT is large, and this can make the PT explode easily for its overheating. Now, during the fundamental or can be the harmonic resonance, the current is not usually large, but the voltage can be shooted at very high level. It can destroy the insulation of the equipment and cause the serious accident. So this phenomena was analyzed in the EMTP software by modeling and simulations, software simulations. Mitigation of the this phenomena was proposed, validated, and then implemented as well. Now, this is the overview and SLD of the thermal power plant, which is here considered for where the EMVT failures has been observed. We can see total 9 units and 2 typical configuration, 330 megawatt and 660 megawatt. We can see here. Now, this particular power plant have this state grid connection, national grid connection, along with the FSC, and other grid also with the HVDC, 500 kV HVDC. Now, the ferroresonance phenomena for the VT experienced mainly here in the 660 megawatt in 4 units, 4 different units as well. It has been not experienced in 30 megawatt because the VT is not installed in particular configuration that we will see later. So mainly this is the VT configuration. Here we can see the generator is connected with the system with the NGR. So it is a highly resistive grounded system for its obvious for its application. And this is the main PT, 3 kind of PT which we are using in this power plant. So this is the one PT which have the open delta core. And this particular PT star point is connected with the system ground. This is the other PT, which is a 2 PT, we can say. It has open delta core, but for specific particular application called the interturn protection. But the star point of this PT is not connected with the system ground. It is connected mainly with the generator neutral point to derive the interturn fault. And this is a 3 PT which doesn't have the open delta core. So if you see here, the PT which experience the ferroresonance, this is the 1 PT. Because as we mentioned earlier, it is the star point of the PT is connected with the system ground, and it has the uh, low resistor device connected in the open delta core. So as we understood and documented, this ferroresonance phenomena occur when a ferroresonance magnetic core inside the electrical device, primarily the voltage transformer or unloaded power transformer, operate in the saturated condition, under which inductance mainly become a nonlinear element. Now, in practice, this ferroresonance can be triggered even by a temporary introduction of the core into saturation, which can drive in that mode. For example, it can be result from the switching operation or a change in the voltage uh, because of the earth fault occurred. So this ferroresonance as a source of disturbance and failure in power system is very dangerous due to its consequences. Mainly, we can say it does the significant saturation of the core, so it can lead the thermal damage of voltage transformer's primary winding, and ferroresonance itself develops the high over voltage. And during this phenomena, the neutral point is increased at the some voltage level, which makes the zero sequence voltage appear in the system, which we observed here, and it can falsify the operation of the ground fault protection itself, which is a fundamental protection for the generator stator. Now, before moving forward, it is important to know the construction of the EMVT itself and the associated factor, which is generally used in power plant. So EMVT mainly are designed to prevent a negligible load to the supply being measured and have an accurate voltage ratio and obviously phase relationship to enable accurate secondary connected metering or a protection device. Now the standard voltage ratio is 110 volts, compatible with the standard measuring instruments. And the burden and accuracy are also usually stated as a combined parameter due to they are dependent on each other. But mainly the protection or metering style PT designed with the smaller cores and VA capacities than the power transformer. So with that, it can saturate at the lower voltage output and can save the connected metering devices from getting it damaged due to the over voltage spikes observed during the grid because of the many disturbances. So we will go through the case study of the generator line side VT failure, which experienced, as mentioned, 4 incidents of this EMVT failure connected to the generator were observed. Now, before the occurrence, actually machine was connected with the grid and running smooth. And suddenly that conventional stator for 95% was operated and it got tripped. So after that, all the checks of primary and secondary circuit, including device, the connected cables, transformer, the circuitry itself, where checks all performed, including IR and winding resistance measurement, everything. But no abnormality found with all the investigations. And no trace of the actual ground fault was captured. Machine was under outage, so it was very important to identify the issues. Therefore, further checks and tests of the VT circuit then performed. And during this test, during the winding resistance measurement, everything is found okay, but except that VT1 that we have seen earlier, that one particular phase, Y phase can say, primary winding was not behaving normal. It is the data shows the abnormal results. So leakage current test and all that perform, and then finally conclude that VT1 Y phase generating some high leakage current at the rated voltage, and that can create the ground fault scenario. So particular VT was replaced by spare one and then machine taken in service. But after that, based on the DR, as actually the actual ground fault not observed, but based on the DR and the waveform captured from the relay, from the oscillograph, and the type of the failure observed, this ferroresonance phenomena was concluded as a root cause of the VT failure, which can be described like that. that switching operation of the no load voltage transformer, in this case, this VT have a very low burden on the open delta core that involves the small inductive current and inrush current, and then consequent generation of the over voltage that can actually damage the insulation over time of that particular VT, and that was connected in the star configuration. So after that, certain action has been taken. For an example, measurement of the power quality parameter at specific locations, and the power system simulation in EMTP was carried out for present study and to evaluate the mitigation technique as well. So the failed VT inspected further and demolished for his internal inspection, because from the from the outer side, it doesn't feel any damage, I mean, occurred inside. So it demolished, and these are the certain images of the PT, which is inspected further. So here we can see this insulation, that carbonized insulations we can see here. So this has been observed during this PT. And the failure of this kind of what we can see here, it's identical in almost all the 4 PTs, which has been subsequently failed. Here we can see the insulation fail. This kind of image is captured that time. Now let us go into some more detail to understand the this particular phenomena, ferroresonance better. Now in the linear resonance, we can see here that only occurs in the circuit. It consists the series or parallel connected this component, resistor, inductor, and capacitor. And when the source is tuned to the natural frequency of this circuit, but the capacitive and inductive reactance of the circuit are identical at the resonance frequency. Now, capacitance reactance of this circuit and I mean in the linear or even otherwise the parallel resonance mainly occur when the inductive and capacitive reactance of the circuit exactly balance. So inductive reactance is mainly proportional in the frequency, while capacitive is inversely proportional. So the resonance frequency for this circuit can be found in which the inductive reactance and this capacitive reactance exactly cancel each other. Now, but for the ferroresonance, this is not the similar case, but things are not quite same in the linear non-linear circuit when happen in the linear resonance. So if in the linear circuit, this particular element is if it replaced by the non-linear inductor, which represent the ferroelectric material, then circuit can be referred as the ferroresonance. Now, this particular ferroresonance is distinguished from the linear resonance in many ways. For example, there exist several stable steady-state responses to any given change of the parameter. Now, resonance at a given frequency can occur over a wide range of the parameter values. The resonance frequency can be different for each stable responses. Now, in a linear circuit, the resonance condition occur at only one frequency, which is a fixed value of L and C. On the other hand, the non-linear circuit can exhibit multiple values of the inductance when this core is driven into the saturation. Therefore, this implies that there is a wide range of the capacitance, and that can potentially lead to the ferroresonance. So this is the EI characteristics of the ferroresonance, which you can see here. And the relationship between multiple values of the saturable inductance and the increased capacitance can be seen here. Now, based on this particular phenomena, as we discussed that the fundamental element involved in the ferroresonance circuit are a resistance, capacitance, and the nonlinear inductor. The development of the resonance circuit taking place in the power system is mainly due to its reconfiguration during the fault or during some switching. This particular change is caused by the switching events immediately after the switching event, when the initial transient over voltage will firstly occur, and this is followed by the next phase of the transient, where the system may arrive in the another more steady state condition. So due to the non-linearity of this ferroresonance circuit, there can be several steady state ferroresonance responses can randomly occur into the system. So basically, there are 4 types of steady state response a ferroresonance circuit can possibly have. Mainly, they are fundamental, subharmonic, periodic, and chaotic mode. So in this mode, this particular resonance has the same period as T of the power system, and the frequency spectrum of the signal consists the fundamental frequency component, and the dominant one is followed by the decreasing component of the odd harmonics. So fundamental is maximum, and then third, and then fifth and seventh, and then followed by the nth odd harmonic. In addition, this type of response can also be identified by using this stroboscopic diagram, which can obtain by the simultaneous sampling of the voltage V and current I at the fundamental frequency. Now, the subharmonic type of resonance has a period of this NT, which is a multiple of the source period. Now, this fundamental mode of the ferroresonance, which we have seen earlier, can called a period of 1. But the resonance, ferroresonance with a multiple submultiple of the power system frequency has a period called the N ferroresonance. So this frequency contents are described having a spectrum of the frequency equal to the f0 by n, with f0 is denoting the fundamental frequency and n is can be represented as an integer. Now with this signal, there are n points exist in the particular diagram, and it signifies the predominant of the fundamental frequency component with decreased harmonic content at other frequencies. Now this is a third mode. In particular, this mode, this kind of signal is not a periodic signal. This the frequency content in this signal are discontinuous in the frequency spectrum, whose frequencies are defined as NF1 plus MF2, where M are integers and F1 and F2 are the irrational real number. So this type of response displays feature employing a closed cycle of the dotted points on the stroboscopic diagram. Now, finally, this mode has a signal exhibiting a non-periodic with a continuous frequency spectrum. I mean, it is not cancelled for any frequencies. This stroboscopic plot we can see here, it consists of the n points surrounding an area, which is known as the attractor strain rejector, which appears to skip it around normally. So like that, we can see different modes. Now let us see the how ferroresonance can occur in EMVT, which is the main case here. Now this is the equivalent circuit of the EMVT, how it is connected in the system. So during the voltage transform of ferroresonance, an oscillation occurs between the nonlinear inductor of the VT and the capacitance of network remaining or the connected with the VT. Now in this case, the energy is coupled to the nonlinear core of the voltage transformer via circuit breaker getting capacitance to sustain the resonance. Now the VT can be driven into saturation, resulting in the high current at subharmonic or a fundamental frequency. Now, during simulations or even field also, very high voltage of the very high voltage up to 4 pu can theoretically arise in worst case condition. Now EMVT have a relatively low thermal capacity, and overheating can result in the insulation failure very quickly. So this is the phenomena. Now we have discussed ferroresonance so far. Now let us discuss how it can be prevented or mitigated. Now ferroresonance can be prevented by eliminating one of the precondition. It can be avoided or prevented before actually it happens. It needs some design change itself. Accordingly, for example, we can use the delta connected primary VT. But in this case, we need to take care of the protection system because main protections are derived from the star connected PTs. Now, we can also prevent the system becoming the ungrounded main system. But for the generator application, we need to take care of the fault current, which are passing through the generator stator core during the ground fault itself. Now, we can also design a VT to operate at a much lower induction value. So the saturation point can be at least twice of the system voltage. So these are the design related changes. But once ferroresonance has set in, it can be stopped by removing the condition that it make it sustain. So for an example, by restoring the power to the transformer, that ferroresonance can be stopped. Now, sustained ferroresonance sometimes be avoided by loading a transformer, mainly secondary, with an appropriate resistive or a reactive devices, which is a standard norms. However, by introducing these losses by means of permanent load resistance can affect the system by absorbing the power and can affect the metering accuracy as well. Now, the load connected across an open delta is much more effective than a load connected in a usual way. And it has the additional advantage of avoiding power dissipation during normal balance operation. Now, the appropriate specification of this particular resistance is very important, uh, uh, and which is provided by this load. But here EMTP simulation can help to arrive at the uh, appropriate resistor value. Now, as we have seen, the Ferroresonance phenomena is one of the most complex phenomena in the field of the electromagnetic transient. Once possibility of the ferroresonance is established, deciding whether the ferroresonance resonance will occur or not, or if it does, how severe it effects could be, it requires us simulations and by solving a complex nonlinear problem. Now, therefore, time domain simulations seems to be the reliable tool to solve this problem and to assess the effectiveness of the countermeasures. So the computer program most widely used to simulate the power system transient in general and the ferroresonance in particular can be the EMTP software for accurate studies on ferroresonance phenomena in power transfer instrument transformer. The software tool must be capable to provide a facility for deionization or reionization of the transformer, determination of the core eminent flux, a precise modeling of the VTCTs and other devices, accurate modeling of the machines, and the efficient design of the control system for power electronics based drives by taking into account the machine non-linearity and actual power loss. The EMTP software tool offers all these functionalities and capable enough for this type of studies involves the complex phenomena. As mentioned earlier, the appropriate specification of the load resistance requires the help of computer simulations, and EMTP software tool does it very well. So based on the power system network of the particular thermal power plant, it was simulated in the EMTP for Ferroresonance study. All the relevant components were modeled in detail, including generators, cables, isolator, potential transformers, including its saturation characteristics, interrupting devices like circuit breaker, timing of the interruption, and the sequence in which the phase are open and closed that are also important. Then other device like current transformers, all are model. The single line diagram of such a stream can be seen here. The substation equipment such as circuit breakers, CTs, PTs are represented by this straight capacitance to ground. After modeling the system component, the circuit breaker close open for specific time intervals. For an example, for 45 milliseconds and after 550 milliseconds with or without ground faults. And the waveforms at the input voltage, I mean before the circuit breaker, and the waveform at the HV side of the PT, LV side of the PT has been captured and analyzed. So the result of the simulations in the form of capture graph we'll see in the next couple of slides. But before that, uh, we can see here, this is a basic circuit to show some aspect of the new reactor model in the ferroresonance phenomena. So in this test, what can be seen, this source voltage gradually increased and to the point that ferroresonance occurred. Uh, and then it is gradually decreased to a zero. So first waveform is the voltage during the test. When ferroresonance occur, the VT voltage does drastically went up to the transient peak of the 2.36 pu here, and then settled down up to the 1.94 pu. So after ferroresonance is eliminated, the VT operating point returns to the normal condition. So this figures is the close-up of the VT voltage and power loss during the transit period from normal to steady state resonance circuit. So the result of the simulations for the particular power plant model in the form of capture graph can seen here and next couple of slides. So these are the waveforms of this result got from the simulations. These are for some more simulations has been done and can be seen. So there's the voltages, and here we can see the system voltage also and the current captured by the CT. So these are the waveforms of the EMTP simulations. So as we have seen, by adding the load resistance or a saturable reactor or similar device in VT circuit, the resonance can be prevented or mitigated. However, it can affect the performance of the protection system by drawing more current, and it causes the excessive load to the VT circuit, so which may affect over power system as well. So use of the damping resistor in the open delta connection of the auxiliary winding of three individual VTs is a simple solution that is mostly used, but it is not fully efficient in many cases because the resistance needed to efficient damp the ferroresonance oscillations should be very small. But on the contrary, it draws too much current and cause excessive load to the VT. Furthermore, the simple damping resistor connected permanently to the VTs, which may affect earth fault protection, conventional earth fault protection due to voltage drop in open delta configuration caused by the damping resistor itself. So all of these disadvantages can be handled by connecting a smart device, which can see here, it's a VT Guard Pro. In the VT open delta winding, actually it enables the application of the damping with variable resistance. It also allows setting of the voltage threshold to operate the device itself, and it work with the protection in a tandem manner by providing the configurable time delay to set the burden connection. Now, using a damping resistor or VT guard in open delta winding shows considerable reduce the risk of the ferroresonance itself. So this device belongs to advanced protection family, which protects the VT against the ferroresonance phenomena by proper and prompt damping action, as we can see here in the waveforms, without creating excessive power consumption, as in case of the using the ordinary damping resistor during a normal operation of the network. So these are the without device waveform, and this is the after damping provided by the device itself. Now, this image shows the operating principle of the device, which we are discussing. During the first part, the equipment offer the low resistance. Then after warming inbuilt PTC thermistor, the equipment rise its resistive value to protect the voltage transformer again overloading. After the earth fault is eliminated, the VT guard needs actually a certain time to cool down and lower its resistance value. So it can be observed that after the VT guard triggered, the current and voltage resumes to its normal value after providing the proper damping action. So nominal value of the damping resistor is very important for effective and quick damping. As we discussed earlier, with the EMTP simulations and test results, it is possible to visualize and comparison between the different values of the damping resistor for its effectiveness against the ferroresonance. So simulation model for testing and effectiveness of the ferroresonance damping with a different value of resistors was done, and results can be seen here. And resistance value needed for effective damping in the ferroresonance for particular model for ferroresonance oscillations requires very small, less than 20 ohm in this case. So these are the waveforms of different damping resistor values. Now, by using a damping resistor of such a low value, it can result in a risk of the thermal damage of the VT during abnormal network condition, which can arise during a prolonged earth faults. So resistor having a very small value would cause overloading of the VT during earth fault. So this is why this particular device increased its ohmic value from 15 or 20 ohm to 200 ohm for the 100 volt feed voltage. So these are additional characteristics which normally doesn't offered by the permanent load connecting devices. So this image shows the actual setup which is needed to test the whatever device we suggested for this, its efficacy to damp the ferroresonance oscillations effectively. Now, this test setup consists of the actual EMVTs connected in phase to ground with the voltage source. The capacitance can also be seen connected in the test circuit. The VT guard or device which is under test is connected in the open delta winding of the EMVTs. Now, to arrange this type of actual test setup is a slightly difficult job altogether. And in this image, the actual damping can also be seen, which is provided by the device during the ferroresonance. So these are the voltage and current waveform, the before and after damping. Now, this is the waveform of the actual test setup. Now, as we have seen, the arrangement of the actual setup is very difficult at site, and to even test each device in detail. However, this performance evaluation and functionality test of the individual device is also possible with EMTP simulation and transplay of the component which is generated from the simulation, and we can play these components through the secondary test kit, which this setup has been seen here. The VT-Guard device was tested in the site laboratory. Test setup can be seen here. And the objective was to test the operation of VT-Guard device in parallel with the existing generator protection device, and to confirm the operation of the VT guard during ferroresonance condition and the operation of the protection relay in case of actual ground fault occurs. So various components were transplayed, which was generated from the EMTP simulations, and efficacy of this device has been evaluated. It has been observed that if the three-phase voltage are balanced in nature, the zero sequence voltage uh, if the three-phase voltage are balanced in nature, the zero voltage appear across the VT guard terminal, open data winding. So no current will flow and device remains inactive and offer high impedance in the circuit. But as soon as the voltage across VT guard increase above these some values, it offers the low impedance path in the circuit and ground path to the harmonics. And by this way, it dissipates the oscillations energy, which is generated by the resonance itself. So this is the snapshot of the various components waveforms transplayed through the test kit, which is actually generated from the EMTP simulations, mainly to test the VT guard functionalities. So what we have discussed so far that can be summarized in this way. The ferroresonance phenomena may take place when the core of an inductive device becomes saturated and its current basically flux characteristic becomes a nonlinear. The undamped ferroresonance oscillations are dangerous to the equipment and potentially lead to permanent equipment damage. The phone number of EMVT failure experienced in particular thermal power plant. This EMVT failed was installed in the typical configuration. The risk of the EMVT failure can be prevented or mitigated by connecting device effective damping resistor in the open delta winding. The simulation of the ferroresonance is quite complex, but is possible and demands the time domain simulation, but it is possible effectively with the EMTP program. And this specification of the damping resistor can also be ascertained with the help of the EMTP simulations. EMTP simulations is an effective tool to obtain the ferroresonance phenomena, which can get the same result from the actual setup of the EMVTs and other equipments. The efficacy of this solution proposed can also be validated with the EMTP simulation. The VT-Guard application and its adequacy evaluated with the help of the component transport, which is actually generated from the EMTP. The after satisfactory evaluation device has been connected in EMVT in open delta winding. And finally, the supply of the ferroresonance mitigation devices has been considered for our new thermal power plant at the designing stage itself.